Hello everyone. Today we're going to talk about what energy is and how energy, work, and power are related, and the two types of energy. How are energy, work, and power related? Did you put a book in your backpack this morning? If so, then you did work on the book. Work is done when a force moves an object. The ability to do work or cause change is called energy. Work and energy. When you do work on an object, some of your energy is transferred to that object. You can think of work as the transfer of energy. When energy is transferred, the object upon which the work is done gains energy. Energy is measured in joules, the same unit as work. Power and energy. Power is the rate at which work is done. Since the transfer of energy is work, then power is the rate at which energy is transferred, or the amount of energy transferred in units of time. Here you can see the formula. Power equals energy transferred divided by time. Different machines have different amounts of power. For example, you could use either a hand shovel or a snowblower, like the one in Figure 1. You could use that to remove from your driveway the snow. Each transfers the same amount of energy when it moves the snow the same distance. Again, there's the shovel and there's the snow blower. Each transfers the same amount of energy when it moves the snow the same distance. However, you could move the snow faster using the snow blower than the hand shovel. The snowblower has more power because it transfers the same amount of energy to the snow in less time. What are the two types of energy? Moving objects, such as vehicles shown in Figure 2. Here we have two cars and a motorcycle. A rock perched on the edge of a cliff or a stretched rubber band has another type of energy. There are two types of energy, kinetic energy and potential energy. Whether energy is kinetic or potential depends on the motion, position, and shape of the object. A good rule of thumb for everyone is this: kinetic energy is energy of movement, potential energy is energy of rest. Kinetic energy: a moving object can do work when it strikes another object or moves it. For example, a swinging hammer does work on a nail as it drives the nail into a piece of wood. The hammer has energy because it can do work. The energy an object has due to its motion is called kinetic energy. Factors affecting kinetic energy. The kinetic energy of an object depends on both its speed and its mass. Suppose you're hit with a tennis ball that has been lightly tossed at you. It probably won't hurt much. What if you were hurt with the same tennis ball traveling at a much faster speed? It would hurt. The faster an object moves, the more kinetic energy it has. And I'll say that one again. Faster an object moves, the more kinetic energy it has. Kinetic energy also increases as mass increases. And just a reminder, mass is the amount of matter in an object. It is not weight. Suppose a tennis ball rolls across the ground and hits you in the foot. Compare this with getting hit in the foot with a bowling ball moving at the same speed as the tennis ball. The bowling ball is much more noticeable because it has more kinetic energy than the tennis ball. The bowling ball has more kinetic energy because it has greater mass. Now there's a formula for kinetic energy, and it looks like this right here. You can use the following equation to solve kinetic energy of an object. says 1/2 times mass times speed squared. Another way to write that, students, is this. Kinetic energy equals 1/2 mv squared. V is velocity. You'll learn in physics, if you have not already, that speed and velocity have the same formula. The difference is the velocity has a direction. So please keep that in mind. Now, my suggestion to everyone, if you're not comfortable with 1/2, the decimal equivalent is 0.5. So you could write it like this. It's important to keep in mind that when you're solving for kinetic energy, to make this easy on you and make sure you don't make a mistake, square the velocity first before you multiply times mass and then times 0.5. So think of it like this. You read left to right. This particular equation to solve, start at the right and move to your left. And all of it is multiplication after you square the velocities. Here's the example they have for you. It says, for example, suppose a boy is pulling a 10-kilogram wagon at a speed of 1 meters per second. So we're looking for the kinetic energy of the wagon. So 1 squared times 10 kilograms times 1/2. So 1 squared is 1 times 10. 10 times 1 is 1. I'm sorry. 1 times 10, I had it backwards. 1 times 10 is 10, and then times 1/2 is 5. Now, the units for joules is kilograms, meters squared, second squared. That's equal to 1 joule. So that's where you come up with 5 joules. Okay? Do changes in speed and mass have the same effect on kinetic energy of the wagon? No. Changing the speed of the wagon will have a greater effect on kinetic energy than changing its mass by the same factor. Okay? Let me say that again. Changing the speed of the wagon will have a greater effect on kinetic energy than changing the mass of that object. This is because speed is squared in the kinetic energy equation. For example, doubling the mass of the wagon will double its kinetic energy, but doubling the speed of the wagon will quadruple its kinetic energy. Okay? Let's talk about potential energy. Potential energy, this is when an object does not have to be moving to have energy. These are situations where the object is at rest. Some objects have energy as a result of their shapes or positions. When you lift a book up to your desk from the floor or compress a spring by winding a toy, you transfer energy to it. The energy you transfer is stored or held in readiness. It might be used later if the book falls or the spring unwinds. Energy that results from the position or shape of the object is called potential energy. Now, you can see this down here. I was going to talk about this. There is also potential energy related to gravity on this planet. This type of energy has the potential to do work. Okay? Now, gravitational potential energy, or GPE, as it's sometimes abbreviated. Potential energy related to an object's height is called gravitational potential energy. In other words, the height off the ground. The gravitational potential energy of an object is equal to the work done to lift the object up to that height. Remember, work is equal to force multiplied by distance. So work would be this formula here. Okay? The force you use to lift the object is equal to its weight. The distance you move the object is its height above the ground. You can calculate the object's gravitational potential energy using this equation. GPE, gravitational potential energy, equals weight times height. For example, suppose a book has a weight of 10 newtons. If a book is lifted 2 meters off the ground, the book has 10 newtons times 2 meters, or 20 joules of gravitational potential energy. which would look something like this. When you come over here, equals weight times height. So the weight would be 10 newtons times the height of 2 meters, 20. And we know it's going to be joules. Just like that. Okay. Down here at the bottom, we've got some rock climbing pictures, 4 different individuals. They have different weights, 400, 600, 400 again, and 600. And you can also see here the height going up, 6, 5, 4, 3, 2, 1 meter. So what you would do there is determine the height of each climber by this scale over here and multiply it times their particular weight. Another type of potential energy is elastic potential energy. An object has a different type of potential energy due to its shape. Elastic potential energy is the energy associated with objects that can be compressed, which means squeezed in tighter, or stretched out like a rubber band. For example, when a girl in figure 4 presses down on the trampoline changes shape. The trampoline now has potential energy. When the girl pushes off the trampoline, the stored energy sends the girl upward. Gets on the trampoline, presses down, stored energy pushes the girl upward. Okay? So that's all we're going to discuss for right now as far as the types of energy. We hope you enjoyed this reading, and we will continue at another time. Thank you. Goodbye.